The topic that we'll be talking about today is mechanical waves and the general properties of mechanical waves. So, before we get into the main factors and the properties of the waves or the wave equation, it's really important to understand what waves are and how they occur in physics and in our real lives. So, there are several kinds of waves, and several kinds of waves occur in physics. Mechanical waves are produced by a disturbance, such as a vibrating object in material medium, and are transmitted by particles of the medium vibrating to and fro. Such waves can be seen or felt and include waves on a rope or spring. Water waves and sound waves are also an example of waves. These water waves and sound waves in air or in other materials, they can also propagate in other materials. So we'll be mostly studying about their propagation in air though. So as I initially said that there are different types of waves. So by that I meant that the two main types of waves are uh, transverse waves and longitudinal waves. Now what exactly classifies them to is the movement of their particles. So in transverse waves, the movement of particles is basically perpendicular to the direction of the propagation of waves. However, in longitudinal waves, it is parallel to the direction of the propagation of waves. In both of these waves, the particle is basically vibrating or moving in to and fro uh, direction or motion. However, the wave propagates in a continuous manner. So, the progressive or traveling wave is a disturbance which carries energy from one place to another without transferring matter. There are two types of transverse and longitudinal. Now we will be further discussing what transverse waves are and some examples of transverse waves in our lives and how we can really create them using our hand or demonstrate them. But why exactly is transverse waves different than longitudinal waves? So what happens is that in transverse waves, as you can see that there are particles over here and there are particles over here. Let's just assume that this wave is traveling in this direction and so is this wave. Now, although the wave is traveling in this direction towards the right, but the particles aren't moving towards the right. They're basically moving up and down. So this particle over here, at this instant, it is at this point. But at the next moment, it's going to be somewhere here, and then here, and then here, and then gradually here. So basically, the movement it has done is in y direction. However, the wave is propagating in x direction clearly. That is why we say that in transverse wave, we're going to talk about this in more detail so that it is easier to understand and capture the movements of each particle in transverse waves and in longitudinal waves. Now, if we talk about longitudinal waves, in these waves, the particle moves like in this wave, the particle moves like this. So that's like up and down of motion. However, in this wave, the longitudinal waves, although it is moving in the right way, in the x direction towards the right, the particles move in the x plane in the x direction too. I'm sorry, this is not in the same plane. It got a little twisty, but it's basically yeah. So the particles move like this, vibration to and fro vibration. So this is like a spring, a slinky, which is moved in this direction. As you can see, there are areas where the spring coils, they are closer to each other or they're mushed together, and then there are areas where they aren't that closer together. However, this as in this area, you can see that the distance between the two coils is maximum, and in this area, the distance is really minimum, and they're just really touching each other. So these are the areas that are created in longitudinal waves. Similarly, there are some areas like this one. It is above the neutral line, and then this is below the neutral line. So these are some characteristics of longitudinal and transverse waves themselves, and we're going to talk about them. So moving forward. In a transverse wave, the direction of disturbance is at right angles. In a transverse wave, the direction of disturbance is at right angles to the direction of wave travel. A transverse wave can be sent along a rope or a spring by fixing one of the end and moving it rapidly up and down. The disturbance generated by the hands is passed on from one part of the rope to the next, which performs the same motion but slightly later. The humps and hollows of the wave travel along the rope as each part of the rope vibrates transversely about its undisturbed position. Water waves are also transwaves. So the reason why we see ripples or the way a wave travels is because of the transverse wave motion, which is like this. And we see these upper parts of the, basically the waves in water more clearly, which are called um, crests. As mentioned here, they're written humps and hollows, but the physical term of these two parts, let's just say, if a wave is like this, and this is the neutral mean line right over here. Then this right here, the part above the neutral line, or this line over here, it is called crest. CREST, crest, and the other one, the part over here which is below the line, it is called trough. TROUGH. UGH. So this is crest and this is trough, and that's how the wave propagates. Now, one of the ways we can demonstrate it in our real life is that we take a cloth or a rope, and then you fix it at one end, then to the other end that is not fixed, you make these continuous up and down motions. That that will demonstrate the transverse waves, and you'll be able to see that similar shape is formed by the rope itself, and it's forming crests and troughs in the air through that rope. As we were talking about transverse waves, I thought it was important to basically understand the way it propagates and the particles move. As you can see that let's just say if we localize ourselves to one point, it'll be easier to understand the movement. It is really clear that the wave is moving in the x direction, and that this is the propagation of wave, or if you look at it in another way, then this is the propagation of wave, whatever. But the thing is that it is propagating in the x direction. However, if you think about these particles that are mentioned over here, then you can see that the particle over here goes over here. So basically the propagation that is happening is in x direction, but the particle movement is in y direction, which is perpendicular. Now we are going to get to the main topic, that is describing waves and describing the main properties of waves and how they behave in different materials and what phenomena they can basically exhibit. So there are a few terms that we should be familiar with, including wavelength, frequency, speed, and some other terms. So let's just first get into wavelength. Wavelength of a wave represented by the Greek letter lambda. This is the notation that we give to wavelengths. Is the distance between successive crests. Now it's easier to say that it is the distance between successive crests, but what exactly does a wavelength mean? For that, I'm gonna draw this demo little diagram over here to basically. Okay, so if we have this wave, this did not look very smooth, so I'm gonna delete this and look at another one over here. So first of all, let's just say we have this line. Okay, this is like a neutral line or something, and now it'll be easier to draw the waves. Okay, so the wavelength of a wave represented by the Greek letter lambda is the distance between successive crests. Now, what exactly does the distance between successive crests mean? So this crest starts over here. So we're talking about this, and we are talking about the distance. So it's going to be in meters or centimeters, whatever the unit we take. But we're talking about SI units, so let's just go with meters for now. So this is the start of the first crest, successive crest, it says. So the next crest is going to be this crest. So we started off from the initial start point of the crest, so we are going to end at the start of the next successive crest. So this basically is the wavelength. The distance between these 2 points is the wavelength of the wave. But if you look closely, this distance right here represents one complete wave. So that is one crest and then one trough. Similarly, if you take the distance from the first trough from over here, let me just change the color from, sorry, not even this, from over here, from this point to this point, which is the second trough, the start of the second trough. Again, similarly, we can see that this distance basically totally includes one crest and then one trough. So wavelength is the distance that includes one complete wave or one crest, one trough, or the distance between two successive points in phase. Now, what do I exactly mean by the word in phase? I'm going to write it here, phase. Or even in phase. So, what does in phase exactly mean? So, in phase is basically that if you have, I'm going to draw this initially, this wave at first. Okay. Initially, we were talking about 2 points in a wave. Uh, Number one was at the start of the first crest, and the other one was in the start of the successive crest or the second crest right after. Now you can see that the point, the basically the point or the position of these two points, let's just mark them A and B, is similar. That is, both of them are in the start of a crest. Let's just say we don't take these 2 points, but we do take a point over here and then a point over here. Will the distance between this point and then this point also be a wavelength? Yes, it will be. So wavelength is basically the distance that is between two successive points in phase. Similarly, if we take a distance between this point and then this point, well, this is also a wavelength. because this is half the crest, and then this is half the crest, and this is a complete draft. So you know what, if we take 2 points in phase, it is going to two successive points in phase, it is going to give us the wavelength of a material. Okay, now we have talked about wavelength, and now the next thing that is important to talk about is the frequency. So the frequency f is the number of complete waves generated per second. If the end of a rope is moved up and down twice in a second, 2 waves are produced in this time. Okay, so again, I'm going to draw the wave. And this time, what I'm going to do is that I'm going to draw a graph. So over here, we are seeing seconds, and and over here, let's just say we have amplitude. So that is in meters. And I'm going to talk about the amplitude too, what exactly amplitude is. So what happens is that initially wave starts at this point and then it propagates further. Frequency is the number of waves that can be generated per second. So if we have 1 second over here, and then let's just say if this is 0.5 seconds, this is 0 seconds. It depends on the marking on the basically the graph itself, and then this is 1.5 seconds. Now what is going to be the frequency of the wave? For that, if we're given a graph, first thing we do is that we go to the point where it is marked as 1 second. So we have marked it over here, and then we count the number of waves that have been generated from the time 0 to time 1 second. So if we start from 0, from this point till this point, we have one wave because these 2 points are in phase, and then from this point to this point, we have another wave. So 2 waves are formed in 1 second, and thus that tells us that we have a frequency of 2 hertz. Another way to go about it is that we look at the time period of the wave. Now, time period is another property of wave that we generally talk about, and time period is basically the time it takes for a wave to pass or propagate one complete wavelength. So if I start from here and I talk about one complete wavelength, so over here, so this is one complete wavelength. The time it takes for one complete wavelength is 0.5 seconds. So I'm gonna write this. 0.5 seconds for 1 lambda. Sorry. Um, I'll have to draw that again. So it's okay. Just make a rough sketch. The thing that I was basically saying is that time completed for if time taken for one complete wavelength is, let's just say, as we saw, 0.5 seconds, 0.5 seconds for time period. So frequency is the inverse of time period. 1 by time period gives us f. So 1 by 0.5 will give us 2, and 2 is the frequency of this wave. That is the conclusion that I was talking about. Now we've talked about wavelength and speed in wavelength and frequency in detail. Now we're going to talk about the speed. The speed v of the wave is the distance moved in the direction of travel of wave by the crest or any point of the wave in 1 second. We usually generally talk about the crest because it is easier to just mark one point and convenience and use it every time. Uh, but it is valid for any point. We can just take one single point, any single point on a wave, and then observe it. That how much distance does it travel in 1 second? So that basically gives us the speed, which is really a simple idea. However, amplitude is a new thing. Amplitude is the height of the crest or the depth of the trough measured from the undisturbed position of when it is carrying the wave, such as the rope. So you've seen that I draw this line first. By drawing this line, I'm basically drawing this undisturbed region, and then over it, I'm going to draw the wave. So in the graph, we saw that this side was amplitude, which is being measured in meters, and this side was time, which is being measured in seconds. So amplitude is basically this distance till the highest point, or this distance till the lowest point. So the amplitude is the maximum height of the crest or the maximum depth of the drop. This basically shows everything that we have already discussed. So you can just go through this. It shows wavelength from this point to this point because these 2 points are in phase. They are at the same point but successive waves. And then this A is basically the amplitude, and this is trough, this is crest. Everything is properly labeled. Now we've talked about the term phase, but we're going to talk about it again. So the short arrows at A, B, C, D on figure show the direction of vibration on parts of the rope at these points. The parts at A and C have same speed in the same direction and are in phase. And B and D, the parts are also in phase with each other, but they're out of phase with those at A and C because their direction of vibration is opposite. Now, how do we basically measure the direction of particles? Now, in this case, the wave is moving in this direction. That is because if we start from here, let's just say start from here, and the first point that we experience or we see is point D. Okay. If wave is moving towards the left, the particle D is going to go like this. So initially its movement is going to be upwards. And particle C is going to go like this. So initially its movement is going to be downwards. And then part B is going to go like this, so its movement is going to be upwards. So part B and part D, they are in phase with each other because they are in the start of a trough and both of them are moving in the same direction. They are going to move, or their direction is upwards. However, if we talk about A and C, they are in phase with each other, but they are out of phase with B and D because their direction is opposite. So it was pretty simple to basically understand what exactly it means. Now the wave equation. The faster the end of the rope is vibrated, the shorter the wavelength will be produced. That is, the higher frequency, the smaller its wavelength. There is a useful connection between F, lambda, and V, which is true for all types of waves, which is FV is equal to F lambda. So the frequency of the wave multiplied by the wavelength is equal to the velocity, and that is the wave equation. Now, what are wavefronts and waves, and why do we need them? So in two-dimensional, a wavefront is a line in which disturbance has the same phase at all points. The crest of wave in a ripple tank can be thought of as wavefronts. A vibrating source produces a succession of wavefronts, all of the same shape in a ripple tank. Straight fronts are produced by a vibrating bar, a line source, and a circular wavefronts are produced by a vibrating ball or a point source. Line drawn at right angles to wavefronts is called a wave. So if this is a wave, and let's just say it's water, so what we can see is only and only um, this part above, because we can't really see the depressions. So a point that basically joins this these lines, it's called a wavefront. And if you look at it from the top, it just appears as one line. So that is a wavefront. However, the line that shows that is perpendicular to the wavefront, let's just say like this. So if we have, let's just say, a lot of waves that are going like this, and hence a lot of wavefronts, this wavefront, then the line perpendicular to them is called a ray. So this blue one is a ray, and these green ones on the top of the crest, they are wavefronts. WF, I'm going to write. Now we have talked about the features, the basic properties of waves. Now we're going to talk about some phenomena that they exhibit. So in straight water, waves are falling on a metal strip placed in a ripple tank at an angle of 60 degrees. We are going to observe that in the next slide, as there is going to be a picture. The perpendicular to the strip at the point where the incident ray strikes is called normal. The wavefronts are represented by straight lines and can be thought of as crests. They're at right angles to the direction of wave to the rays. The direction of the angle of reflection is also 60. Incidence at other angles shows that the angle of incidence and angle of reflection are always equal in case of reflection. So let's just look at it very simply. So initially we have these waves that are traveling, this wave, and this wave. So instead of showing them in form of waves, we've just shown them in form of wavefronts, because it's easier to basically imagine like that. And the way I drew, that was also not the best way, because you can't really see the drops. So they basically draw some wavefronts and then an incident ray through them. So 3 wavefronts are enough, because the other ones are also going to be at the same distance as this distance, and then like this. So it was better to draw a ray that was in the perpendicular direction to the wavefronts. As you can see that this ray is perpendicular to these wavefronts at all points. So the ray touches the surface, or the metal strip, that is the reflecting surface, and it is incident at an angle of 60 degrees. So this angle from the normal, from the perpendicular of the perpendicular on the surface, on the reflecting surface, and the ray is 60 degrees. So when it reflects back, it is noted that the reflecting angle, that the reflected wavefronts and the ray that it is formed, they make an angle of 60 from the normal too. So the incident ray angle with the normal and the reflected ray angle with the normal, both of them are 60, and both of them are equal in case of reflection. Now we've talked about reflection. Now it's important to talk about this another uh, thing, another phenomena, that is refraction, and we'll be talking about it in more detail in the next lecture. In a glass plate is placed in a ripple tank so that the water over the glass plate is about 1 millimeter deep, but is 5 millimeter deep elsewhere. So here we're talking about different depths and how does wave react in different depths. Continuous straight waves in the shallow region are found to have shorter wavelength than those in the deeper parts. Now what happens is that in reflection, we did not notice any change in wavelength. Okay, there's another thing to note, that the wavelength is measured from 2 points in phase, or from successive crests. So if you think about it, if this basically shows the first set of crests, then this shows the second set of crests. So the distance between one wavefront to the other wavefront is basically one wavelength. And in this case, there is no difference in the wavelength, speed, or anything. There is just a difference in the direction of incident and reflected waves. However, over here, we notice that the wavelength is basically shortens in the deep apart, and and the wavefronts, they come closer together. Okay, so both set of waves have the frequency of the vibrating bars. So the frequency remains same. Now, if we think about the wave equation, we have V, F, and lambda. So if frequency remains same, lambda changes, then the other thing that must change in order for the equation to satisfy is velocity. So if the lambda has decreased, so has V, since F is fixed. Since lambda and V are directly proportional to each other, so that basically tells us that if V has decreased, lambda has also decreased, since, you know. Hence, waves travel more slowly in shallow water and they travel fast in the uh, deep water. This basically is a drawing that shows refraction, that initially we had some waves that were incident on the water, on the shallow water, and then after this interface change, the their direction changes. Obviously, they change this direction, but similarly, with the change of direction, they also have the distance between the two wavefronts, it decreases and they come closer together, they're squeezed in more. So that is how diffraction works. We're going to get to it more in more detail in the next slides.